Walk onto any heavy manufacturing floor, and the first thing you notice is sheer kinetic force. Massive stamping presses and robotic arms exert tons of pressure in fractions of a second, presenting an immediate physical hazard to human operators. To protect the people working alongside this equipment, factories rely on an array of safety devices. These range from manual emergency stop buttons to automatic, invisible barriers like optical light curtains. Historically, these devices were wired directly into standard general-purpose electrical relays. When an operator pressed an e-stop, it would cut the control voltage to the relay, which in turn disconnected power to the machine. The problem with standard relays lies in their physical mechanics. Every time a relay opens or closes a high-load circuit, electricity has a tendency to jump the gap, creating a tiny, high-temperature arc of plasma. Over thousands of cycles, this arcing degrades the metal contacts. Eventually, intense heat can cause those internal contacts to physically melt and fuse shut. If a standard relay welds closed, it creates a deadly illusion. An operator can hit the emergency stop button, and the control voltage will drop, but the physical contacts will remain stuck together, continuously feeding power to the machine right when it needs to stop. This mechanical reality meant that simply adding more emergency buttons couldn't guarantee safety. The electrical architecture itself had to be redesigned. In 1987, the German automation manufacturer Pilz patented the PNOZ emergency stop relay. This moved the industry away from hardwired standard components and introduced specialized safety hardware. Today, this hardware is deeply integrated into industrial regulations. Engineers conduct precise risk assessments to determine the necessary performance levels for a machine, which dictates the exact type of safety hardware required. The difference between a standard relay and a safety relay comes down to predictability. Safety relays are engineered specifically for deterministic failure modes. Deterministic failure means that if any single internal component breaks, degrades, or shorts, the system will definitively force the machine to de-energize. It fails safely, every time. To see exactly how a circuit guarantees this physical outcome, we have to look inside the safety relay itself, mapping its internal mechanics, its inputs, and its final outputs. The foundation of a safety relay is its internal redundancy. It does not rely on a single switching mechanism. Instead, the unit utilizes two independent internal relays operating in parallel. This dual-channel design ensures that if one channel suffers a mechanical failure or shorts out, the second, independent channel remains physically capable of breaking the circuit. To prevent the relay from resetting if one of those contacts welds, the system uses positive-guided or force-guided contacts. Inside the relay, the main switching contact and an auxiliary monitoring contact are permanently connected by a solid physical bar. When electrical arcing causes that primary, normally open contact to melt and fuse shut, the circuit remains closed. But because they are rigidly bonded together, that welded primary contact physically blocks the secondary, normally closed contact from ever shutting. This mechanical lock acts as a permanent physical alarm. The open monitoring contact breaks the internal logic circuit, instantly preventing the machine from being restarted. This redundant internal logic relies on a precise stream of data coming from the outside. That data arrives when external safety devices connect to the relay's dual-channel inputs. Take a standard emergency stop button. The safety relay sends out a continuous, pulsed electrical signal from a terminal like S11. This signal passes through two completely independent contacts inside the e-stop, and then returns to the relay at terminals S12 and S14. The relay's microcontrollers actively evaluate these returning pulses. When the button is pressed, the relay verifies that both channels break the circuit at the exact same time. If the physical wiring degrades over time, causing the two input channels to fray and short together, the pulse timing returning to the relay changes. These test pulses allow the relay to function as an active diagnostic node. It identifies cross-circuits and wiring degradation as they occur, catching faults before an operator even attempts to use the safety switch. Not all safety devices use physical mechanical contacts. Modern automated cells often rely on solid-state electronic sensors, like invisible optical safety light curtains. Instead of physical switches, these electronic devices communicate with the safety relay using what are known as OSSD signals, or output signal switching devices. This chart shows the voltage profile of an OSSD signal over time. It maintains a steady 24-volt high state, but continuously executes micro-drops, plunging the voltage to zero for just a few microseconds before returning to normal. These micro-drops are so brief that they don't actually trigger the machine to shut down, but they are long enough for the safety relay to constantly verify the integrity of the line. If a stray 24-volt wire shorts against the OSSD line, it flatlines the signal at 24 volts, deleting those tiny drops. The relay immediately detects the missing pulses and triggers a stop. OSSD integration gives the safety relay the ability to continuously verify complex, solid-state electronic parameters with the exact same rigor as a mechanical switch. Once the internal logic validates the inputs, it passes the command to the output stage, exiting the relay through specific safety terminals, like 13 and 14 or 23 and 24. These safety outputs don't power the machine directly. They route control power to the heavy-duty external motor contactors that handle the massive voltage required to physically spin the equipment. But this introduces a final, critical vulnerability. The safety relay is highly protected inside its casing, but what prevents those external high-voltage contactors from welding shut under heavy loads? To solve this, the circuit relies on a process called external device monitoring, or simply the feedback loop. Every time the external motor contactors close, their normally closed auxiliary contacts open. This auxiliary path is physically wired in series directly back into the safety relay at a terminal like S21. If one of those external high-power contactors welds close, its mechanical link ensures the auxiliary contact remains permanently open. This severs the feedback loop entirely, and the safety relay physically locks out the reset button until the faulty contactor is replaced. Through the feedback loop, the relay projects its deterministic failure guarantee outside of its own casing, monitoring the health of the final high-voltage actuators down the line. A single motor only requires a basic setup, but large-scale industrial machinery demands far more safety outputs than a single relay can physically hold. To scale the architecture, safety relays use a method called daisy chaining. A base relay unit utilizes its own validated safe outputs to drive the inputs of additional expansion modules. This multiplies the available control circuits while keeping the entire network under the same diagnostic umbrella. However, integrating these complex networks introduces a dangerous opportunity for human error on the factory floor. Occasionally, an installer will wire a safety switch directly into the main A1 and A2 power supply terminals of the relay. When the switch is tripped, it simply unplugs the entire unit from its power source. By completely killing the power, the technician bypasses internal microcontrollers, the test pulses, and the feedback loops. They take a sophisticated diagnostic instrument and downgrade it into a basic, unmonitored power switch. When wired correctly, the sequential architecture works as a single unified nervous system for the machine. The logic flows sequentially, from the secure power supply into the safety sensors, evaluated by the relay's dual-channel logic, out to the monitored contactors, and finally engaging the heavy machinery. The LED indicators on the front face of the relay, tracking supply voltage, switch states, and semiconductor outputs, serve as a real-time diagnostic dashboard for this entire chain of events. The relay cannot stop physical parts from wearing down, and it cannot prevent wires from shorting out over time. Its true purpose is to ensure that when those electrical and mechanical failures eventually happen, the system detects them instantly and forces the machinery into a safe, de-energized state. This level of rigorous architectural design is a legal and practical requirement across all sectors of modern manufacturing. You find these specialized circuits managing high-mass material handling systems, actively protecting operators working underneath heavy overhead bridge cranes. They are equally critical in high-speed manufacturing environments, continuously verifying the perimeters of automated robotic work cells. This is achieved through specific, verifiable technologies: parallel internal logic, force-guided contacts, external device monitoring loops, and micro-pulsed OSSD integration. By utilizing hardware engineered specifically to anticipate and catch its own faults, safety relays take the unpredictable mechanical hazards of heavy industry and enforce deterministic safety, reliably protecting operators every single day.